Everybody, let me welcome you back to the second week if you were here last week, and if you weren't, welcome anyway. The first speaker this morning at the beginning of the mini course is Danijela, who will talk about methods for studying abelian action and centralizer.
It's a very, this is the first time I see this big restaurant. It's like a movie theater. It's also really fun. Okay. Also, I learned from Felix that it was his initiative that thank you, Felix. Because the other one was yeah, it was very nice. Okay, so our phone, yes. Well, I was told that there are 3 microphones. I'll try. Is it loud enough? But when I turn to the board, it will not be as loud. So don't turn. Okay. So Disheng and I will give this course. So the plan for the course is, we do have a plan. So the plan for the course is, I'll give you a plan because I think it's good to know what to expect and what not to expect. Right. So the plan for the course, I will start actually by trying to give you some kind of a picture through examples. So I'll go through many examples, and I will try to introduce the basic structures that we use in the study of abelian action through examples. So then, so many examples. Invariant structures. Main results. That's probably something that I will try to do today. Maybe results in restricted environment. Then what I will try to do next time is to show you some methods. In simple cases. So we'll go through 2-3 methods maybe, whatever time allows. And then I will talk more about more methods again. More about centralizers. So, and then Disheng will speak about more methods. Rather, yeah, some of this will be generalization of what I talked about here, so it will be connected, hopefully. Okay. So, so the basic setting is smooth dynamics. Compact manifold. Smooth. And the object that we would like to study is the group of symmetries, the group of smooth symmetries of F. So let's call it Z. So this is the group of smooth diffeomorphisms. Smooth symmetries of F. So what's a symmetry? A symmetry you can take the coordinate change, which doesn't really change your map at all. So it's maps which commute to the F. But it's nice to think about them as maps which coordinate changes, which do not change at all the map, because then you can derive immediately physical properties. So in other words, the centralizer. Okay. So then the question posed by Smale. I don't know when, maybe 70, was that, first of all, notice that the centralizer always contains powers of the map, so always contains the subgroup generated by M, always contains the Z subgroup. So the question that Smale posed was, I guess, coming from the fact that imagine that if you have enough very complicated dynamics, chaotic, very complicated order structure, then it should be very hard to keep it, to preserve it with order chain. So Smale's question was, is it true that typically in C1, in CR topology, yes, yeah, that's true. Okay, that's true. Yeah, it could be V or a quotient of V. Okay. Yeah. Could be V or a quotient of V. Okay. So is it true that typically in CR topology, the centralizer is just the group generated by X? And so this question was answered positively in C1 topology by Bonatti-Crovisier and Wilkinson. So this is kind of typical behavior. So this is not what I'm going to talk about at all. So we're not interested about typical behavior. So we're interested trying to write bigger in atypical behavior. What do I mean by atypical situation? Atypical situation where the centralizer is somehow large. And I'll explain in example what I mean by large. So what do we want? What is the main theme? The main theme of this whole lecture series, main theme is the following. And I put a quotation because nothing is complete. You know what I'm saying? So if F has somehow complicated, has complicated dynamics, to some extent, we want, and the centralizer is somehow large. Does this give us, when does this give us that the map is very special, that F is the infinity conjugate to an algebraic model? So this is like the general question that we would like to address. Okay, so we call this if it happens, this phenomenon, if it happens, you will see that it does happen. We would like to call it centralizer rigidity. So big and large centralizer plus some complicated and then implies smooth particles. Okay, so now I want to say, first of all, what are the algebraic systems? So I'll try to describe what happened, what are the notions we have. So algebraic systems. Okay, so here the manifold is going to be a Lie group factored by a lattice. Gamma is couple part, or singularly. A lattice will be such that G mod gamma is compact. And the dynamic is going to be either what how can we get easily, so interactions are right translations, while these left translations basically the gamma gamma V and then V is some translation, or one thing to do with automorphisms, because the lattice is an automorphism preserving lattice gamma preserving. Then A depends on automorphism of homogeneous space. And so algebraic math or affine, so affine math are compositions of translations and automorphisms. If we act just by length translation, then it is homogeneous math. If we act by translation on a doubly homogeneous space, that's also we like to call algebraic. Another case. Algebraic. When you add, you have the space V mod gamma, and then you have a compact group here, and then you factor by the compact group. So if you take a left translation, where G commutes with this compact group, then it goes through and you get the action or map on this bihomogeneous space. So these are bihomogeneous examples. We will also talk about the algebraic. So this is explaining what do we mean by an algebraic model. Okay. So I will say that the source and the notation, the definition, any action that is smoothly conjugate an algebraic model also smoothly algebraic. So action smoothly algebraic. These things we need to conjugate to an algebraic model. So what else in that vague statement is not clear is what is the complicated dynamics we want to consider. Here. What is the complicated dynamics? So maybe it's not. Use the other boards for consider. So what do I mean by complicated dynamics? So this is what this conference is kind of meeting to about. So F will be partially hyperbolic. So we'll have a the usual Danijela bundle splitting into stable, unstable, and center. And in all the situations that we will talk about, the center will actually be integrable. So stable and unstable are always integrable, but the center will also, in our example, be integrable. It's not always integrable. The foliation with C1 leaves. Okay, so the usual. What? Yes, remember. Thank you. So there exists the foliation here as well. Okay. So the property that will keep coming back in everything I'm talking about, that will be important. I want to mention now, I mean, everybody knows, but okay, this is a course. So F is accessible if any 2 points unequal can be connected via a stable, unstable, broken path. So this is what we will often use. So this is kind of like the basic setup before we go to them. Yes, the broken path means that you start with a point, another point, and you have a possibility to reach, to go from one to the other by going through leaves of stable and unstable, and so on. It will it's not fitting in the description of F, but it's going to fit in the general picture. It will be important. Yeah. Okay, so now yeah, exactly. Yeah. So we will see now examples which are accessible, which are not accessible. So example. I kind of I had too many examples, so I put them in groups. So the group one, group one is simple. So 1A, I labeled them because I want to refer to them later. It's not a bad idea if you're taking notes of something to remember the label. So 1A is just take the usual hyperbolic map. Hyperbolic automorphism. And this one. The centralizer. And hyperbolic automorphism. So the centralizer of F is just itself and possibly a finite group. So in that case, we say it's virtually D. So that's fairly easy to see. That's a general statement about calculation. This means it's better than this. So this means virtually D, which also means that it is D after a finite limit sample. So maybe it's a finite group of samples. Anyway, that's the one example. One big example is so common. So F by diagonal subgroup. Yeah, subgroup is the group of maybe and by representation, so this is an algebraic model. And if you take time one map, for example, of this flow, that is the name, so phi 1 is a partially hyperbolic map, and its centralizer is R. Huh? Yes, yes, first program. So this is forgetting to go. Okay. Okay, so the first two examples, what we know when we centralize it, we know that, for example, the first map, it has structural stability, right? It will preserve, if you take the stability flow, for example, like time changes, right, and it's called and it's change the dynamics. So those are rank 1 models. So there's nothing, the centralized group is really not B. It has rank 1, it's B or R. Now we try to build examples now which have bigger centralizers, which have higher rank. So the next class, for example, naturally is labeled by 2A. 2A example is just take a product of A and A. So F is A. Then you can see that any A to the K, B to the L commutes in F. So the centralizer, yeah, no. Okay. So the centralizer is going to contain KL with everything in V2. Is going to contain this V2 sample. Is that all? Is the centralizer bigger? Okay. But then you know. Thank you. It's bigger. It's a bit bigger. It contains also this matrix. So this parabolic matrix is also, or group generated by, is also inside of the centroid. It's not nice how I'm written it, so try to fix it. D of F also contains this subgroup. These do not exactly commute, but it's like a semi-direct product. So these two, that's the centralizer. So it's big. It's big. Now let's go to the example 2b. 2b is the example where I take the geodesic flow and I take a product of two such things. So I will get the R2 action. Okay? So we take diagonal action acting by left translation on SL2R mod gamma cross SL2R mod gamma. And the diagonal is now by left translation. And diagonal is now e to the t, e to the minus t, cross e to the s, e to the minus s. Okay, and we have the diagonal group is isomorphic to R2, so we have a higher rank action. What is useful, and this is what I'm going to explain kind of for half an hour for in general situations. What is useful is to have a picture in the acting group to illustrate how all the elements act. So right now we can study this one or we can study another generator, but it's very, very useful, as you will see, hopefully, to actually see how somehow illustrate how the full action looks like in the picture. So one way to do it, and the way to do it in the use, is this. Let me arrange the parabolic right here because I'm not gonna talk about it so much. Okay. So let's go to this one. This is the acting. Let's take just the D2 component of the action. Let's forget about the parabolic for a moment. And I want to draw a picture, which is it big enough? So Z2 is the lattice in here. So this is my Z2. In the Z2 lattice, I have one coordinate, which is A identity, and the other one, which is A identity. So here somewhere I have A. Here somewhere I have A. And so all the points in this lattice are elements of my action. All of these are in my action. And then when you have this picture, you can kind of try to analyze how much hyperbolicity I have in this picture. So here we can observe that if I take anything which lies on this line, it's actually not going to be hyperbolic. It's not even going to be ergodic. It's identity rotate. On this line, same thing. A cross identity and identity rotate. And so I have these two lines, and I observe that for these two lines, both of these two lines are not ergodic. Not ergodic. And now, if you want to be, if you want to draw a picture for the full centralizer, remember the centralizer had its parabolic part, then you have one more direction here, and everything in this direction has zero Laplace form. It's just parabolic. Okay, so I'll put a green dot for the extra super parabolic direction, which is kind of here. Okay, so let's do the same for the product. Let's do the same for the product of the geodesic flows. Yes. 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 You're right. And plus all the accumulated the same parabolic guys and continuing one here is like A to the n. So A to the n. Exactly. So to be example was product of geodesic flows on SL2R mod gamma. So the picture here will look kind of similar. So we have a product. So whenever you're, so except that now this is R2, the picture is sitting in R2. And if you're on this line, you will see identity to this point. Same as before, is identity cross the usual geodesic flow. And same here. So on both of these lines, again, we see no ergodism. Yes, 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 yes. What I want to do. So G1 we take cross identity. And here we take identity cross G1. So G1 is the time one. I called it phi. Phi 1. Phi 1. Time 1. Okay, so we have two lines again, and both lines are not ergodic. And if you look at both pictures, if you pick any other line here or any other line here, it is going to be ergodic. And moreover, it is going to be normally hyperbolic, in this case, to the foliation R2. And in this case, it's just going to be hyperbolic. So in this picture, all the elements which are not on these non-ergodic lines are ergodic, are not only ergodic, they are hyperbolic. So all the elements not on the lines are Anosov. Here the same, all the elements not on the lines are going to be normally hyperbolic with respect to R2 foliation, the orbit foliation of the product action. Yes. Can you say one? Yes, yes, the power measure. Thank you. So everybody not in the line is going to be normally hyperbolic. With respect to R2 diagonal foliation. The homogeneous foliation given by the diagonal action. So that's the picture for these product examples. And what we see here is that in both cases, the picture tells us we have non-ergodic lines, and it also tells us that it's pretty clear that we have a factor. We can factor the action here to just the rank one case. We can factor the action here to just the rank one case. Okay, so let me define the rank one factor in general, because this is what we will want to avoid. So let me do the definition. General definition. How am I doing the time? Okay, so definition. So suppose that RK cross GK S on manifold M. Yeah. Okay, now let's say K plus L be equal to Q for then it makes sense. The definition. Yes. A CS rank one factor. There exists the following data. We have the following data. So we have a smooth manifold. Let's say M bar and a CS subversion. Phi from M one bar, is the factor. And we have a projective automorphism sigma which goes from the group into some finite extension of R or Z. So into some group which is let's call example H, where H is a finite of R or Z. No, I want actually finite extension for the factor, yeah. And we have a local thing. Yes, actually. Of this group on L bar, such that the diagram comes from phi of the action G on F is sigma G, this is now H, and times phi of F. This is our initial actually. So this is simply the diagram from the central diagram. Like this. And you project, and here I had the action of RK cross DL, but now I factor it to some R or Z actually, and decide of it. K plus L and there just because that is named, like it says something new. Okay, so what I want to say is that these are the situations we would like to avoid. Okay, so in fact, what I will call higher rank actions will be actions which do not have factors like this. Why? So ZK plus RL is higher rank. And I'll write usually like this. When K plus L is bigger equal than 2, and no rank 1 factors. Of course, I define it with CS. I define the CS rank 1 factor. Which one do I mean here? Let's say, for now, let's say no C infinity rank 1 factors. So sometimes it will be different. Okay, so now we go to examples. Yes. An action, a smooth action. Exactly. Thank you. Okay, so now we go to examples which are high rank in this sense. So these are class 3 examples. 3A. Exactly. So observe all examples up to here are not high rank. They have rank 1 factors and obvious ones. So example 3A. Example 3A is a high rank version of example 1A. So here we take a torus and we take an automorphism. And actually, before I tell you general thing, if I do even, let's say on T3, take an automorphism which is hyperbolic, which automatically means that it has 3 eigenvalues, not only in a circle, and simple. And then it's fairly easy to see, okay, that is a general statement, that such things have the centralizer, which is virtually Z2, which is affine. So this is the group generated by 2 such maps, where B is also hyperbolic. And this example is good to remember because I'm going to keep coming back to it. So let's draw the picture here. Okay, what's the picture here? The picture here is this. So this is the Z2. A has eigenvalues lambda 1, lambda 2, lambda 3. B has eigenvalues mu1, mu2, mu3. The fact that two matrices commute makes the eigendirections jointly invariant. And so in this jointly invariant direction, if you look at A, K, B to the L, so arbitrary elements of the action, will in one of the eigendirections, V1, V2, V3. We look like that lambda I to the K, mu to the L. And so how this action looks like, if you try to draw the picture, it will still be a lattice in here, but this lattice will not be integer. So in other words, it will not intersect, what I want to say, it will not intersect this line. Okay. So what happens is that every element of this action is going to be hyperbolic. So the line, yes. So first, these lines are just K equals 0, L equals 0. So these are just these zero lines. But then I have, I'm not pointing to the correct lines. So what I wanted to draw is this. So elements of my action indeed lie here. So this is A cross identity cross A. This is B. Just A, okay. A, B. But now I have, yeah. What? Yes, yes, yes. Yes, yes. Okay. So you want to put L here and K here. A square and so on, B square and so on, and then you have this lattice of elements which are acting, that's fine. And now the important lines, which will be kind of characterizing the action, will not be passing through this line. So the important lines will be lines where this is 0. Okay? Where this is 1. So where this is 1. In other words, we don't have anything in this action which has the upper exponent 0. But we do have lines, lambda I to the T, mu I to the S equal to 1. So these lines will be important for what's coming. So let me draw this somehow. So this line will be, for example, S log lambda 1 plus T log lambda mu 1 equals 0. And so on. So we do it for every eigendirection. So let's define it. So chi 1 of ST, is chi I is S log lambda I plus T log mu I. So these are functionals which live on R2. Yeah.
Is it possible that the lattice is also backward?
It does not actually. That's exactly the case. So if you look at this line, if I did have an element here, it would mean that I have 0 entropy. Okay, in this direction. But that I have 0 exponent in this direction. But I don't. In this action, no element has 0 exponent in any direction. It's an algebraic thing. So these things will never be thrown. But so kernel of psi I are these lines. Let's call them something. Let's call them L I. So this is a line. 1, 2, 3. And the action actually never crosses one of these lines. All the elements in the action are unknown. So for every KL, for every KL, AKBL, and the corresponding element does not lie on the line. KL is not on LI for any I. So we do have though the property, which also is algebraic thing. We do have the property that elements which lie in the action, so these are all the what? Yes, it's a number theoretic property. Yes. The number theoretic property, I would like you to accept it without me proving it. So the thing is that the V2 action inside of this picture, the one I'm studying, is actually getting as close as you want. You can find elements as close as you want to the lines. Why? Because the lines are irrational. Moreover, they're algebraic. I mean, they're algebraic. The lines are irrational, but all the other elements are Anosov. So everybody outside of the lines is Anosov everywhere. All of these are Anosov. Okay, so the last example, I guess. Really slow. Yeah. 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 Yes. So what you're asking, I'm going to explain next time. This is going to be about properties of these invariant directions for the action, and I do it next time in detail and jump in. But now I want to say one more example, so that this one doesn't end there. So and now I'm starting to get nervous because and my program has to be 3B. 3B is take the diagonal group and act on SL QR cross SL QR, but mod an irreducible lattice. What does it mean irreducible lattice? It means that I cannot factor this into M1 plus M2. So then the same action. So so now the picture will look like this. And it's the same in a sense, right? So I will have, I don't want to give a color. I will have this line where in the groups I see identity across the diagonal. I'm painting the picture again for our article. But now this is going to be a body. So there is a general statement called Mausner's epodicity statement for translation on semi-simple groups. When the lattice is reduced by itself, all of these elements are actually bodies. Every line in the diagonal group as a radical. This is representation here in that. So we have this line, but now they have a radical. And any other line is a body. These lines are still non-hyperbolic. But they're not normally hyperbolic. They're not normally hyperbolic. To the orbit college, to articulate. Not hyperbolic. Otherwise, not normally hyperbolic. Okay, and last example, I really didn't even get close to what everything I want to say. Last example, and one equal statement. And then I'll stop. And I'll come back to the last example. So if you're not, then next time I'll say. So three things. Is the Smale version of that. And I'll explain it in much more detail. So here I take the diagonal double and I add on SL3R. Not double. The diagonal double here is going to look like e to the 1, e to the 2, e to the 3, where Pi, the sum of Pi is 0. Anyway, so here 0, so this is isomorphic to R2. So I can draw similar in the picture. Okay. Again, I have line ST. In this case, it will be parameterized by R2. But now, this is the diagonal action on SO3R. In SO3R, typical points we have looks like that. These are very important. And then when you multiply by a matrix like this, similar thing happens as for the ordinary geodesic flow. So you multiply this, and then depending on what these numbers are, some of these unipotent directions are going to expand and some are going to contract. And so things actually can be included in the picture. So let me write it like this. So E to the C1, they expand. For example, U X and U1, 2 by factor E to the T1 minus T2. Over that. So if T1 is equal to T2, this will be an isometric direction. If T1 is bigger than T2, this will be a standard direction. If T2 is less than T2, then you get such a place on this by expanding contractively by this path or splitting that. So what are now the important lines? The important lines are exactly where T1, for example, is equal to 2. Then I have an extra direction where I'm not normally hyperbolic. So here we'll have lines like that. T1 to 2, to 3, and T1. So on these lines, I'll have elements which have extra geometric direction. But otherwise, in all the other chambers, all the other cones, I will have normal hyperbolicity to the R2 diagonal action. So here we see that the lines, these important lines, are also ergodic. These are ergodic. Mark one ergodic. But here we see even more. This is even strongly even more hyperbolic than the previous example. Why? If we go here, the stables and unstables are here. These are important. These lines, therefore, will not be accessible. They are not accessible. Not only they are not accessible. And if you go this line, and you pick an element here, maybe these two uniforms will be asymmetric. But then you have plenty of others which generate the whole group, and you still have a disability. This is the last. And so, 30 seconds. I know, it's nice. I was late, no, for 30 minutes. 30 seconds. This is kind of nice to say in the end of the story. I was pointing to these ergodic lines, and that every line is ergodic and so on. So what's the connection? So proposition. Suppose you have an R2 action, and N. I'll leave you with this proposition to prove it as an exercise. Every line in R2 is ergodic is actually equivalent to no measurable rank 1 factors. So this is what we would like to see. And for next time, what I will do what Amy, the question Amy was asking. So I will give you a general picture. If we have an abelian action, what are these invariant structures? What are these lines in general? We need to work with where we don't have rank 1 factors, and how does it help us? So this is exercise to prove. I'm not joking. It's really simple. Yeah.
Since we're running a tiny bit late, maybe we can postpone the questions until a later date. There is an announcement or two.
Thanks. So new week, new announcements, and what's most exciting, new lists for you to sign up. So on Wednesday, we will have an excursion to Rogalin Palace and Museum and walk in a park, but a much shorter walk, as I was told, than the one last week. So if you want more details, ask Felix. And if you want to participate, just add your name to the list. That's the easy part. More difficult part is that we need to gather the info about